In today's lesson, we will learn about the fuzzy logic control system, in which the basic foundation need to be the same with respect to the normal fuzzy logic concept, but we implement that thing specific for the control system problem. But first thing first, let's recap a bit some theoretical foundation about the control system. So basically, in a control system, we usually focusing on the closed loop control system, in which we can optimally setting the thing based on the tuning the controller properly. So in the pretty standard closed loop control system, so we will have this type of the component, in which the first part is the controller, and then the second part will be the plant, and then later on all the things will be fed back to the system. So in this case, we label this thing as the input, so this part as the output. So this is where the controller, in this case we use the fuzzy logic controller, and this is our plant. So usually the plant can be a second order system, third order system, or the first order system. So in the standard closed loop system, the feedback value will be negative, and then this part will be positive. This is the summing junction of the equation. So for this system, so this is where we tap the error that we will use in order to determine the performance of the system. So in this case, error will be determined based on input, which is the positive part, minus the output. So this is the calculation of the error, pretty standard calculation of the error. So the second parameter we can calculate from this thing. So let's say for the error, I will label that thing as P. So the second part that we can calculate or we can utilize in order to tune the performance of the system is based on the delta error. So delta error means that the calculation of error at the current time minus calculation of the error previously. So this is the delta E calculation. So from this pretty standard control system, so let's say if we just focus on the small part, which is we just focusing on the control part of the fuzzy logic. So in this particular case, for the fuzzy logic controller, the input will be, the first one is the error, and then the second one is the delta A. I just use the capital letters in order to make the things much more neat to illustrate. And then once we have the input, so we have some output here. So usually in this case, let's say we label this thing as the delta U. Delta U means that the change of the output with respect to the given input. So in this case, we put our output as the delta U. So for this case, we put here is the delta E, and then both input will be fed to the fuzzy logic controllers in order to determine what is the appropriate output for this particular condition. So basically, from the basic notation of the control system, one of the common parameters to measure the performance of the control system is based on the transient response. So how we measure that thing? So usually it will be based on, we inject input value here. So let's say the input value will be ranging from 0 to 5 volt, and then in the output, it's supposed to be we get almost the same response, but the output response will be a bit deviate with respect to the input, since we plug in this part to the system. So if the system is really accurate or is very neat, means that you plug in the input, the output will be the same. But this is not the case in practice. So usually we will get something like this type of signal, which we call as the transient response. So for the transient response, this part will be 0 to 5 volt, almost the same thing, but the this type of signal will be utilized in order to determine the system performance. So let's zoom out the transient response. So let's say it is the transient response. So for the transient response, the x-axis is the time, and then the y-axis in this case is the value. Let's say it can be voltage, it can be whatever. So this is the y-axis is the value, in which in this case the steady state condition is supposed to be in 5 volt according to the input maximum value. So if I plot the input value to the transient response, so we will obtain something like this, the signal, in which the blue line denote the input and then the green line denote the output performance. So based on this part, we can actually determine some relation between our error and the delta E with respect to the changing of the output parameters or output signal. So in this particular case, so the error is actually input minus, in this case, our output, which is denoted by the green color, and then our delta E will be equal to E current time minus E in the previous time. So from this two equation, the first equation and then the second equation, we can actually determine some ranging or region in which where this thing happening in the transient response form, transient response plot. So in this particular case, let's say based on this thing, if our input is less than our output, then the error will be negative. The same thing, if the input is higher than output, then our error will be positive. We can plot the region in here. So let's say for this particular region, since this is the steady state condition in which all the input will be the same. So let's say our output will be in this particular location. So in this, if this is our output and then the blue line will be the input. So under this region, the whole region here, the input will be higher, always higher with respect to the output. So we can mark this region in which, since the input will be higher than output, so this is what we call as the region where E is positive, means that the error will be always positive in here. So secondly, if we look at the second region here, so if we plot some output in this region, so under this region, the output will be always higher than the input. So if we utilize this equation, if our output will be higher than input, means that our region here will be always negative. So right now we have marked the region of the E positive and E negative in the transient response plot. So secondly, we need also to find the relationship of the delta E with respect to the transient response. So for the delta E, let's change the color. So for the delta E, so it will be based on the difference of the error in every spatial time domain. So let's say in this location, let's say move up here, make the things move up. So the error in this location minus error previously. So if the signal is moving up, means that for this particular case, our new error will always be higher than the previous error. So in this case, we can say that our delta E is positive. So secondly, in the second location here, means that the signal start to going down from the peak. So in this location, so error in here will always less its previous error. So we can say from here, if the signal is going down, then our delta E will become negative. So in a simple way, for the change of error, for the delta E, if the signal is moving up, then delta E will be positive, and if the signal is going down, then the delta E will be negative. So this is basically some sort of the notation that we will utilize later on in order to construct our fuzzy logic mechanism. So now we have some sort of the idea of how the things work in terms of the level region of the error and the delta E in our transient response. So the next part is that from the basic construction of the fuzzy logic control, so we will utilize the input and output in order to construct our four main domains or our four main modules in the fuzzy logic, which is the first one is the fuzzification. And then the second one is the rule base. Third one is the inferencing. And then the final one is the fuzzification. So this part we cover the center of error, bisector of error. So inferencing mechanism is we utilize based on the input, we construct rule that verify or not. Rule base is based on the knowledge of the system. So in this case, we will utilize the relation between the input and output, which is delta E and E with the delta U. And then fuzzification is this is the process we transform from the crisp value to the fuzzy value. So let's start the calculation of the first part, which is the fuzzification process. So for the fuzzifications, if we look at our control system here, we have two input, which is E and delta E, and then we have the output of the delta U. So for the fuzzification, we need to transform that thing to the fuzzy representation by using the membership concept. So let's say we have the first one is the E, second one is the first one is the E, second one is the delta A, and then the third one, which is the output, will be delta U. So since in the notation of the transient response, we have the error positive, error negative. So we can utilize that thing in order to generate our model here. So let's say we define 0, which is no change in terms of the error, and then we stated here is the positive, right side is the positive part, and then the left side will be the negative part. So for the 0, we tap the value at the 0 location. So the same thing for the delta E. We have the negative delta E, positive delta E, And then of course we will have the 0 delta E. So we will put the same notation here, 0, positive, and then negative for the delta E. So as for the delta U, let's say we utilize the same notation in which if the value of the delta U is 0, so now output will be given to the plant. So it can be the negative value fed to the plant or the positive value. So the same thing, we just take the location where the value will be 0. So the next part is to construct the membership function. So we need to define what is the singleton or what is the optimal value of negative, positive that you want to put in the system. So let's say for the first part, for the error part. So for the error, if we look at in our configuration of the inputs, the maximum value will be 5. Let's say we use the 5 volt. So in this case, we need to decide our maximum deviation of error for negative and positive based on the input of 5 volt. What is the suitable value? It will be based on the empirical. So means that if the selected value unable to solve your problem, so you need to change that thing. So in this case, so let's say for the sake of simplicity, we just put the maximum deviation will be based on the given input. Let's say for the positive will be 5, and then the same thing for the negative, which is the maximum deviation will be -5. So so for the membership function, so let's say for this case, we just use the starting from -5. We use the triangle in order to define the membership for the 0. And then the next part for the negative, let's say we start from the -10 here in the axis. So let's say we use the trapezoid, and then the same thing with the positive. So this is the first membership function for the error. So the next part for the delta E. So since the delta E is the change or rate of change of error, so let's say we assume that the value or maximum deviation will be much more less than the deviation of the error. So in this case, let's say if we just put maximum negative will be -1, maximum positive will be 1. So in this case, the membership function, we utilize the same shape. So combination of the triangle and trapezoid. And then finally the output. So for the output, let's say we just select the maximum output for the negative will be -2, positive will be 2, and then we use also the same shape of membership function. So this is the first step in which we convert from the Cripps falsification, we convert from the Cripps to the fuzzy representation. So the first step. So the next step is to construct the role base. So for the role base, we will use the same notation in which we have two input, and then we will fill up the delta U value instead of the constructed role base. So based on the input parameters, we configure that thing to 3x3. So let's say maybe 3x3 in terms of the matrix. So let's say this is E, and then this part will be delta E, in which we have the -0, positive, So the same thing with here, negative, 0, positive. So the aim is that what is the suitable value that we want to fit to inside of the matrix for the delta u. So how we able to fill up the things properly here? We have three part, negative, 0, positive, that we can fill up inside of this thing based on the input, both input of the E and delta E relation. So in order to fill up this thing, let's recap our rule here, in which it said that for the negative value, what is the suitable output? For the positive value, what is the suitable output? So let's say we start with the first one here. So for the first one, we start with this part. If error is negative and then delta error is negative, so if error is negative, let's say I take this thing as number 1. So error is negative means that we are here, somewhere over here. So and then delta E is negative. Negative means that it's going down. So in order to ensure that the transition response will reach the steady state error, this is a steady state condition, will reach the steady state condition. So we need to ensure that the value here, we will give more negative in order to ensure that from here it will goes to the steady state location. So in this case, we give negative to the output of the transition response. So the next part, if error is 0 and then delta E is 0, so we do nothing because this is the optimal condition. So the next part, this is a location number 3. So if error is positive, we are somewhere in here. And then the delta error is positive, so it's going upward to the steady state, is good, but still in the error positive location. So in order to ensure that we reach the steady state, we need to give more positive. We add more positive, it will add up to the current system, current state, then it will go to the steady state condition. Okay, so now let's go to the another part of the cell. So in this case, error is 0. Error is 0. We are somewhere in here. And then delta error is negative. So means that is going downward. So in order to ensure that it goes to the steady state condition, we must give positive value so that it will go upward. Okay, so the next part, error is positive, we are here. Then delta error is negative, going downward. So how we able to solve this thing? We need to give more positive. We give more positive to ensure that we go to the steady state, so this will be positive. So the next part, this cell, error is negative, we are here. Then delta error is 0, so means that it just move straight here. So in order to go to steady state, we need to give negative value so that it will go downward. So this thing will be negative. So the next part, this cell, error is positive, we are here. Then delta error is 0, just straight line. So in order to go to the steady state, we must give more positive value so that it will go to the steady state condition. Okay, move on to the next part. Error is negative, we are here. Then delta error is positive, going upward. So to ensure that if we reach the steady state condition, we need to give more negative value here to ensure that this trend will be go downward. So we need to give
negative value. So the next part, error is 0. Error is 0, we are here, this thing, in this state. And then later on, our delta error is positive, so means that is going upward. So in this case, to ensure that if we go to the steady state condition, we must give negative value in order to make sure that we go downward. So in this case, we give the negative value. So based on this relation, and then based on the trial and response illustration, we're able to construct the rule base for our system. In this case, we have the non-rules, we have the membership functions, and then for the step number 3 and 4, the process will be the same as the fuzzy logic control system, in which you will utilize the given input value. What is the input value, and then decide which rule that will be fire up, the same thing. And then later on, for the final step, which is the defuzzification. So once we get the overall summation of the membership function concatenation, so we can use the center of error or bisector of error in order to get the Cripps value. So the difference between the fuzzy logic control and the fuzzy logic system means that for the fuzzy logic control system, you have only two inputs. You have the same input here. It's either E or delta E. For fuzzy logic, it really depends. Let's say for the car gearing system, your input will be speed or number of time brake supply. For the aircon system, the input will be the temperature or the humidity. So, but for the fuzzy logic control system, the input will be E and delta E, and then the output will be delta U. So, depending on the application, what is the application? Let's say position control system. So usually it will be the in terms of the voltage value. So the next part, I will show you how we can implement this part, the membership function that we have developed in MATLAB.
Now, I will show you an example in MATLAB on how you can design your own fuzzy logic system by using the fuzzy toolbox. So first thing first, in order to trigger or in order to open up the fuzzy toolbox, you need to type the fuzzy. So after that, you will see this type of the toolbox in which you have the basic configuration. You have one input, one output, and one rule base. So what do you need to do next? Because in our system we have two inputs, we need to add variable into the inputs. So we have now two inputs and one outputs. So the first step is let's label everything. So in this case, this part is the error. Secondly, this is the delta error, DE, and then this part is the DU, which is the delta output. Okay, first thing, the most important thing is that let's say we need to save the file first. Let's say we give the name of the FLC. Select some directory, in this case in the desktop. So once we have the basic configuration, the next part is the fuzzification step, in which we need to construct the membership function for input and output. So let's start with the E membership function. So you can see from here, from our previous example, we have one triangles and then we have two trapezoid. So we can tune that thing in here. So just need to first rescale the range. So since our range for the membership function for this case is -5, 5, and then bigger than that thing. So let's say we put the limit of universe of this course from -10 to 10 for the error. Let's say for the delta E will be, let's say 2, -2 to 2, and then for delta U, let's say 4 to -4 to 4. So we put that thing, the range here for the E will be from -10 to 10, then press enter. So the universe of this course of the membership function will be rescaled accordingly. So for the delta E will be -2 to 2, and then for the delta U would be from -4 to 4. So it will scale accordingly. So next we relabel everything. So the center part will be 0. So this is the triangle in which our membership function for the 0 in this case will be -5, 0, 5. We just put it here, -5, 0, 5. So enter. So uh, for the negative and positive, it will be trapezoid. So we change this thing to the trapezoid membership function. So trapezoid membership function will have 4 values instead of 3. So in our example, negative will be, we start with the -10, -10, -5, and then it will be 0. So in this case, we just put it here. The membership function will be -10 to -10 to -5 to 0. And then later on, the next part, which is the positive for the error. So it will be starting, the membership function will be trapezoid, and then the value here will be starting from 0, and then 5, 10, 10. Okay, so we settle in terms of the E part. The next part is the delta E. So we repeat the same process. So center will be 0, and then it will be distributed from -1, 0 to 1. So this is 0 for the negative, supposed to be trapezoid. So for negative will be starting from -2. So this thing will be -2, and then it will be -2, -1, and then 0. So -2, -2, -1, then 0. So this part for the positive, so the value will be 0, 1, 2, 2. Okay, so next the delta U, center will be 0, so it will be from negative to 0 and 2. The negative part will be from -4, -4, -4, -2, 0. So the positive
trap result, it will be from 0 to 4 4. So we have settled in terms of the first step, which is membership function development in order to convert from the crypts value to the fuzzy representation. So the next part is the role base. So by following the roles here, we construct our own membership function, or sorry, we construct our own roles here. So in this case, this is E, and then this is delta E. So in this case, E negative is negative, delta is negative. So if I can put the roles next to this side, so it will be easy for us to do the process. So we start with here, in negative, negative, and then delta U will be negative. So we add the rows. So the next part is E negative, delta U, sorry, delta E. E is negative, delta E will be 0, then this thing will be negative. So if E is negative, delta E will be positive, the value will be negative. Add the rows. Then next, 0, this one is negative, supposed to be positive. If 0 0, then this thing will be 0. Add the rows. 0 positive, the value will be negative. So the final part, which is E is positive here. So E is positive, negative, it will be positive, positive 0, it will be positive, and then positive, positive, the value will be positive. So we have all the 9 rows constructed. So we can close the membership function. So up until now we have settled up in terms of the everything, so we can look in terms of the inferencing engine. So in this case, this is all the roles that have been constructed, E, delta E, and then the output of the delta U. So let's say if we give some input value, so let's say E is negative 2.58, then delta E will be 0.277. So in this case, our delta U is supposed to be negative 1.3. So this is the output of the falsification step. So we can change any value here. Is positive, delta E will be negative, so delta U in this case will be 2.14. So this is the inferencing mechanism in which it will decide which row should be fired, and then this is where the falsification process happen, in which it will calculate the crypts value of the output. So basically this is the simplest way on how we can design the fuzzy logic controller using MATLAB. So it will be quite straightforward. You can actually utilize, or you can import these rules to the Simulink in order to simulate your control system performance in terms of the transient response. This is the rule surface of everything that we cover, all the constructed rules. So you can try by yourself, and then I give you some simple tasks in which so let's say please do verify whether your calculation will be correct or not. Let's say please give some value of your input. Let's say E equal to 1 point, you can give E equal to, let's say, 1.09, or you can put somewhere
let's say E will be equal to 1.5, and then the delta E will be, let's say, negative 1. So in this case, you can do the calculation manually, and then please look at whether you get the answer of the delta U 2.35 by using the center of area method and also the bisector of the area method. So you can try that thing. You can verify your calculation whether it's correct or not by using this toolbox, so that you understand much more better regarding the process. So that's all. Thank you very much.